This is chapter 1 in the atomic and molecular physics, paper 4, as I said, for the semester 3. This is chapter 1. Title of the chapter is atomic structure. So as yesterday we have seen all its historical background of this subject. Today let us start with this first small derivation or the topic here, that is Rutherford model of an atom. Rutherford model of an atom. Okay, so let's see what this particular concept is. So how Rutherford came across this type of model, and what is his contribution, and what are the things that could be discussed under this. Okay, so yesterday we have seen there is a plum pudding model. Okay, yesterday we have seen about this. This was put by J.J. Thomson, and here in this model we have shown something about that atom consists of an entity here, looks like this. So this is a some region or some space region wherein this positive and negative charges are embedded. So same positive and number of negative charges are embedded there, and this is like a cake in which this cherry or some fruit samples that have been added there. So that is called as plum pudding type of model. That model was thought by the J.J. Thomson. So Rutherford further investigated in this model whether this model is correct or not, and for that he suggested one simple experiment, because as I said earlier, the concept of electron was known at that time. The concept of alpha particle was also known at that time. The concept of scattering, so scattering experiment, that was also known at that time. So Rutherford suggested, okay, so we can write in short, Rutherford suggested alpha particle scattering. So that was his contribution, and he suggested that let's see what happens if we go for this alpha particle scattering, and for that he suggested one such experiment. Actually this experiment was done by Marsden, okay, and some another scientist is there, but we won't go into details of that. And for that he suggested a very simple structure here, some experiment. This is source, alpha particle source, and this is a collimator or the small slit. Okay, this is the lead collimator. This is the source. Alpha radiations are given out in all different directions, and out of that we have to select a particular direction of alpha particles only. So these are the alpha particles entering here, and this alpha particle is allowed to strike one gold foil. This is one experiment shows here, and in this gold foil it is found that now I put here is a spectrometer, or there is one telescope is kept at some air distance. So this is my telescope or spectrometer, microscope, or you can go for spectrometer or microscope, and it suggests that these alpha particles are found in different directions. Some alpha particles directly strikes there, some alpha particles gets reflected like this, deflected like this, some alpha particles gets deflected like this, and some are getting reflected like this. So this is what reflection is being observed by, not reflection, deflection I'm saying. Alpha particles are changing their path, and some of the alpha particles are found to be exactly getting reflected back. So some, I'm not saying all, almost. So in this entire experimental setup it has been observed that 40% of alpha particles, number of alpha particles get deviated by angle of 1 degree. Okay, I have shown this picture to be very large. Actually this much deviation is not observed there. So what is that? These particles, alpha particles, are deviated by this thin foil when this alpha particle is traveling through this, and therefore on the basis of this model he thought that what is happening there. So what would be the picture? Why only 14% of the alpha particle gets deviated by an angle or around an angle of 1 degree, almost 86 particles go undeviated, or they do not change their path, only certain. So one more picture if I draw here, I can show here. If this is a nucleus there, the alpha particles coming here, this goes undeviated. Alpha particle very close to this gets deviated like this, so it goes this way, whereas alpha particle coming here goes back this way. Alpha particle coming this again gets deflected like this. Alpha particle going here goes undeflected, and that's what. So this is what a picture that was thought by Rutherford, and on the basis of that, all these are alpha particles, all alpha radiations, and this is the nucleus. So this idea of nucleus was given for the first time by Rutherford, and he showed that in this thin gold foil, inside this atom there is enough empty space, large empty space is available, and he suggested that in spite of having this model of atom is like this, protons and electric charged particle, electrons and positively charged particles, they are embedded in this type of shape. This type of picture is not possible if this type of phenomenon is being observed in actual experiment carried out. So he suggested that in the atom there is a lot much space is available, empty space is available, and because of this singly very few number of new alpha particles are reflected, 100% get back. So this deflection is almost 180 degrees. This reflection is possible provided alpha particles has a positive charge, and this nucleus itself also have a positive charge, and this type of electromagnetic interaction takes place, that is a repulsion between this positively charged particle, alpha particle, and this positively charged nucleus is coming. So for the first time he gave the concept of the nucleus. So concept of atomic nucleus, concept of atomic nucleus was given by Rutherford. So whatever picture by Thomson, that picture is not like this. So on the basis of his experiment he showed that this particular atom is not like that. In an atom the nucleus is such that almost all the charged particles, positively charged particle in the nucleus, they are concentrated in an atom, they are concentrated in a very small space, that is called as nucleus. And his picture was that this is nucleus and electrons are there around it. So this is what the picture of these are the electrons, and I don't know whether they are moving, they are stationary or like that. So this is what an idea, and this is what a nucleus. So all positive charge material, positively charged nucleus. So this concept was for the first time discussed by Rutherford, and here he said that inside an atom entire space here is empty, because of that alpha particles can directly pass through that, and very few alpha particles which are having direct interaction with this nucleus, which are having positive charge, and that's why this type of alpha particles gets reflected back. So using this particular concept, he derived one such very simple formula in his theory, Rutherford theory. I think we'll just write this formula. So the formula Rutherford obtained, the formula Rutherford please write all these things, because I am going to ask questions over this. MCQs will be asked only these particular things what I am writing here, so you have to be very careful about this. Formula that Rutherford obtained. Formula that Rutherford obtained for alpha particle scattering. Alpha particle scattering by a thin foil. By a thin foil, very very thin foil of gold is used. Thin foil on the basis of nuclear model. On the basis of nuclear model. So what was earlier model given by Thomson? He assumed that atomic model is not like that. Most of the positive charges are concentrated in a very small space and electrons are revolving that. So in an atom, actually he went for that calculations, and he showed that this particular calculations, on the basis of that he could measure the radius of a nucleus of this gold. So all these calculations are done. We are not interested in that, but he obtained this formula on the basis of his theory is this: n of theta is equal to, this is Ni, I'll mention each and everything here, this small n into small t, then z square into e raised to 4th, don't derive this relation, it is not needed, 8 pi epsilon 0, this is square, into r square into Ke, kinetic energy square, multiplied by sine square theta upon 2. Long derivation, we are not needed to go for this entire derivation, but this is what the formula. On the basis of his nuclear model, he predicted that the n of theta should be equal to Ni times n into small t into z square into e raised to 4th, divide by 8 pi epsilon 0 square into r square into Ke square into sine square theta by 2. Where? Now let's see what these quantities are. Where? Let's see one by one. This capital N of theta, this is the number of alpha particles. Number of alpha particles per unit area. Per unit area that reach the screen at scattering angle theta. Scattering angle theta. Now what it means, I'll just show here. This is the thin gold foil and this is my screen here. Now I am just measuring, this is angle here, it is 1 degree, 2 degree, 3 degree, 4 degrees, like that. So in this particular, some of, for example, 3 degree to 4 degree, how many number of these alpha particles are observed in this region? So this is how number of alpha particles per unit area. So take a unit area of this screen. On this screen at a certain value of angle, how many number of particles, alpha particles, are being observed? So these particles which were reached to the screen, so these particles which are maybe deviated but not reflected. So if, for example, if there are 100 alpha particles are coming, out of that 99 alpha particles are reached to the screen, not at same location but at different angles, different locations, and as per location, what is the angle made by that location from this central line, and angle made by that, based upon this angle and for this unit area, how many number of particles are observed there. So only one of the particle is reflected back. So out of 100 alpha particles, one is reflected and 99 alpha particles are reaching the screen. So I am just calculating this. N theta is the number of alpha particles per unit area that reaches the screen at a scattering angle given by theta. Now here, as this Ni is that my 100 particles or total number of alpha particles reach the screen. Sorry, this is the total number of alpha particles reached at screen. So out of this 100, 1 is reflected, 99 is reached there, that is my Ni. And in that, at that particular angle per unit area, how many particles are observed of this alpha particles? That is this n theta. Okay, that is Ni. Then small n is number of atoms per unit volume of the foil. So this is what the number density, actual number density of atoms of the gold, of the thin foil. So we are calculating, so this is a number density, number of atoms per unit volume in the foil. This is small n. Capital Z is atomic number of the foil, atomic number of the element in the foil, Okay, same experiment may be done for different types of materials. One's for gold, one's for silver, one's for iron, one's for any other type of materials. So for each and every material, such type of experiment was done. Based upon that, he invented this formula, which is given by this. Then small r is distance of the screen from the foil. Distance of the screen from the foil. We can identify very easily this. Then this Ke, kinetic energy. This is the kinetic energy of alpha particle. Kinetic energy of alpha particle, incident alpha particles. And then small t is the foil thickness, and as usual, this theta is angle of scattering. So try to understand once again this formula given by here. N of theta is the number of particles that reached on the screen per unit area at a particular value of angle. For example, as I said, if at 3 degrees, take one such area, that is 1 millimeter square. So how many number of alpha particles are observed there in 1 millimeter square at an angular distance of 3 degrees from this line of action or from this x-axis. So that is by n theta. Ni is the total number of particles that reached on the screen, and Ni can be calculated how many are reflected back. So if 100 are incident, 1 is reflected, 99 particles are reached on the screen. So that is what that small n we have written is a number of atoms per unit volume. So we have to calculate number density of that foil. So assuming it's some area, some volume, how many number of atoms may be there, this type of calculation can be done. That is small n. T is its actual thickness. As thickness goes on increasing, more and more number of atoms will come in the path of these alpha particles. So this thickness matters. If thickness is very small, then this number n theta may be large or Ni may be very large. If theta is very large, then this total number Ni will be very small, because most of the particle will get reflected and very few particles will reach at the screen. So that thickness again matters. Z is the total number, atomic number of that particular particular atom, because this alpha particle has two positive charges. Nucleus, it has Z times E plus charges. So this is what is clear-cut interaction between Ze, that is the number of positive charges in that atomic nuclei or atom, and twice E, that is the number of charges of that particular that alpha particles. That's why the Z square E raised to 4, this calculation comes from that, and upon 8 pi epsilon 0 square, this is one constant. R is, as I said here, R is the distance of the screen from the foil itself, that is small r. K is the kinetic energy of the alpha particle incident, multiplied by sine square theta upon, sorry, this is not sine square, this is sine raised to 4th, make a correction there, sine raised to 4th. Okay, sorry, this not this is 2 here. Just a minute, let me correct this. Yeah, and here this is sine fourth, sine raised to 4 of theta by 2, where theta is the scattering angle. So this type of relation was invented by this scientist who is called as Rutherford, and his name was one of the very famous name at that time in the molecular physics or in the physics itself, who could give this type of relationship. And therefore this relationship, so here this n of theta is directly proportional to 1 upon sine raised to 4th and of theta upon 2. So this was result predicted by Geiger and Marsden, according to Geiger, Geiger and Marsden. So these scientists did this experiment, and they showed this is happening, and actual theory of Rutherford theory showed that this number of particles that are deviated or observed on the screen per unit area at a particular angle must be proportional to 1 upon sine raised to 4th theta upon 2. If this theta is very large, then this number is going to be small, and then this number of particles observed will be small. So this number will be larger one, this will be smaller one. So this inverse proportionality between this was predicted, and it was actually found in the but that was predicted by this Rutherford theory, and this was found in this experiment, as I said, Geiger and Marsden and so on. And as I said earlier, only 14% of the alpha particles are scattered by more than 1%. Almost 86% of the particles remain unscattered, and that itself suggests that so lot of space is available inside an atom, empty space is available inside an atom. Almost all the positive charges, they are concentrated in a very small space inside an atom, and that is how the concept of nucleus came there. Okay, so we can write this statement again here as follows. So approximately 14% alpha particles are found to get deviated by 1 degree. 14% are found to be get deviated or scattered by more than 1 degree. Okay, 1 degree, and if it is less than that, it almost goes straight. Okay, that is almost 86% alpha particles do not get scattered. Okay, and that suggests in an atom enough empty space is there. And the interaction between alpha particles and electrons, this interaction is not taken into consideration provided alpha particles have almost 8,000 times mass more than the mass of the electron. That's why this interaction is not possible, and that is not supposed to carry out any change in the alpha particles path. That's why this has been directly discarded. Okay, so that suggests there is an enough empty space inside is there, and thus all positive charges, I'm not calling them to be proton now as of now, all positive charges are concentrated in a very small space called as atomic nucleus. Okay, this is called as a atomic nucleus. So the concept of atomic nucleus was given or discovered by Rutherford. So on the basis of this, his experiment, his experiment in theory and mathematics and derivations, etc. That all these things can be studied if you want, but this is not needed as per my suggestion at this stage. Okay, just try to understand. This is what a scattering experiment was done. Alpha particles were thrown on the gold foil. Most of the alpha particles, 86%, remain unaffected. 14% get affected around 1 degree or more than that, and very few, 1 or 2 out of millions, they get directly reflected back. And this fact was taken by Rutherford further to estimate the size of the atomic nucleus. So his theory was that most of the positive charges are concentrated in a very small space. He called it to be a nucleus, and later on he went on finding the size of the nucleus on the basis of this. Now what is this? Suppose he had given this idea. If this is the nucleus, okay, this is the, I'm drawing very large picture, and this alpha particle is approaching from this side. Now this is alpha particle that is approaching. So when it is slightly putting here or coming here, this is not going to touch this alpha particle, but it will get reflected back because of the net positive charge. So it is Ze plus, and here it is twice E plus. So this is the alpha particle coming, and this is the charge, the nucleus itself. So I can take this distance from this. Okay, so this is the Ze plus, as I showed here. This distance here is nothing but radius. So I can take here for this pair of alpha particle coming in, and this nuclei of the radius r, you can go for small r or capital R, doesn't matter. So that is said to be the radius of the nucleus, and this particular alpha particle, if its energy is very low, then this r will be larger. If its energy is made higher and higher, more and more it will approach close to this nucleus. Even though there is a positive charge, here is positive charge, there must be repulsion, but this repulsion will be occurring in such a manner that it depends upon the energy of this alpha particle. If energy is very large, then this alpha particle can reach very close to the nucleus. If energy is very small, then this alpha particle will go back from here. Sometimes it will go back from here. Because of these positive charges and this positive charge, there will be net repulsion. But this particular concept has been taken by Rutherford. He showed that the alpha particle which is just touching the nucleus and getting reflected back, based upon this type of, now there is electrostatic repulsion, there is the energy associated with that, this is the approximate radius of this nucleus. He did following calculations as follows. Okay, so based upon this, so let us calculate distance of closest approach. The distance of closest approach, capital R, for an alpha particle. Closest approach far of an alpha particle. Okay, that is what this, as shown in the diagram. Alpha particle will have smallest r. Okay, this is the smallest value. When it reaches here, समजा इकडचा alpha particle असेल, it will go like this. So this r would be some later. So this alpha particle which is reflected back in 180 degrees, that alpha particle is to be selected, and this distance approach to be closest approach is to be taken. So alpha have smallest r when it approaches to a nucleus. Okay, have smallest r when it approaches to nucleus head on. Okay, directs in a straight line, nucleus head on, and get reflected back by 180 degrees, exactly changes its path. So whatever its path, earlier path, it gets reflected back exactly in 180 degrees scattering. So this is 180 degrees scattering. Okay, so we can take this particular concept. So at this instance of closest approach, at this instance of closest approach, now let's see what I am doing. The initial kinetic energy of alpha particle, okay, here when it is coming here, it is a kinetic energy, and when it reaches there, the entire energy gets converted into the potential energy, because for some moment it stops here, fraction of second, and then gets reflected back. So at that fraction of second, all its kinetic energy gets converted into potential energy. Now in such a situation, I know the formula for its kinetic energy as well as potential energy. That's what I am equating these two energies at this closest approach. That is the idea he uses here. Entirely converted kinetic energy of the alpha particle entirely converted into potential energy. Therefore I can write this relationship. Therefore kinetic energy initial, that means whatever with energy it is coming here, will get converted into potential energy. And in such a situation where the charges of alpha particles are 2e, charges of the positive charge nucleus is Ze plus. So I can write this potential energy by the simple formula 4 pi epsilon 0, then twice Z into e raised to e square. Okay, this is not fourth because e raised to 2, because here alpha particle has charge twice e and nucleus has its charge to be Z times e. Product of this is twice Z e square, and divide by this closest approach distance is r. So try to understand, all its kinetic energy gets converted to potential energy for a fraction of second, very small time in limit, where it is completely stopped and reflected back. So this potential energy and kinetic energy can be equated, and I'll get this relation. So therefore from this, the distance of closest approach capital R will be, just rewrite the relation for R. It is twice Z into e square divided by 4 pi epsilon 0 as it is, multiplied by Ke initial, kinetic energy initial. You can call this to be equation 1. This can be taken as equation 2. Now in natural origin, now this kinetic energy, initial kinetic energy, can be measured, and if in his experiment he measured this in natural origin. So these alpha particles which are coming from some radioactive material, now natural origin, this maximum Ke is equal to 7.7 million electron volt. Now you are introduced with this unit of energy, that is million electron volts, or if it is converted into joules, it comes to be 1.2 into 10 raised to minus 12 joules. How? You can go for further derivations and further calculations of this. And taking this constant, this value of this constant is also known in electrodynamics, 4 pi epsilon 0. This is called as permittivity of free space, electric permittivity of free space. 4 pi is constant, and this is found to be 9 into 10 raised to 9 newtons meter square per L square. Newtons per meter square per L square. This is again a constant. This value can be taken. Now replace all these numbers and get this R. So his estimate for this type of R is equal to, he found out this to be 9 into 10 raised to 9 into 1.6 into 10 raised to minus 19 coulombs. This is square. Okay, so charge of the electron, of the charge plus E minus E whatever. and this calculation gives you, and if it is divided by this 1.2 into 10 raised to minus 12 in MeV, 10 raised to minus 12, I will get this R will be approximately equal to 3.8 into 10 raised to minus 16 times Z. Z is the atomic number of that nucleus meter. So this calculation shows you any material you can use. If its Z is known, we can find out its radius very easily, or the distance of closest approach is taken to be radius by Rutherford, and on the basis of this simple experiment and simple derivation, he could show radius of such and such element is this, hydrogen radius is this, helium radius is this, calcium is this, magnesium is this, iron is this, so and so. So all other materials can be tested, and thereby one gets this particular simple relationship. For example, for gold, since he used this thin foil, gold foil, for gold foil or gold material, Z is equal to 79, that is the atomic number, and therefore radius of aurum, Au is the symbol, chemical symbol for this aurum or gold, it comes to be 3 into 10 raised to minus 14 meters, very small number. So this is the estimation by Rutherford, who estimated for the first time the size of the nucleus of gold. So on the theory of this Rutherford experiment, based on this Rutherford experiment, he could prove the radius of nuclei of the gold element or the gold atom is almost 3 into 10 raised to minus 14 meters. And if you remember, the atom size is 10 raised to minus 10 meters. This is 10 raised to minus 14 meters, and that indicates this nuclear size is less than 10 raised to minus 4 times less than the radius of an atom. So atom's radius is bigger one, it is in few angstrom, and the nuclear radius is 10 raised to 4 times. 10 raised to 1 means 10, 10 raised to 2 means 100, 10 raised to 3 means 1000, and 10 raised to 4 means 10,000. So nuclear radius is 10,000 times smaller than the atomic radius. So this important conclusion was made by Rutherford on the basis of this experiment as shown here. Okay, thus Rutherford proved or showed that the nuclear radius is 10 raised to 4 times smaller than atomic radius. So this is how he showed that this nucleus is very small, and so in general this idea, this is the atom itself, in this is what in few angstroms, 10 raised to minus 10 meters, and on the basis of this is just a very small, and radius of this is 10 raised to minus 14 meters. So here in this atom a large empty space is there. So this is what empty space, and all the mass and the charge of the atom is inside this nucleus, and electrons are moving like this. So this is what the concept he showed. So these are my electrons, but I didn't know at present how these electrons are there, so how they remain inside this nucleus, that concept was not known there at that time. So you can understand, going from this atomic theory, that means from this particular experiment, how the concept of nucleus was developed, how the radius of the nucleus is measured experimentally, what was predicted, what was theoretically predicted, and what was experimentally showed, these things matched, and then this concept of atomic nucleus was well accepted by the scientific community at that time. Till then the concept of nucleus was not known. Nowadays we know this concept very well, or in all details, its constituents, its structures, its properties and everything, but getting this concept of nucleus was not that easy at that time, because that type of modern science was not there at that time. The measurement devices were not that advanced, other electronics and everything was not at that time, no computers and nothing. So this was one such a great discovery by a scientist or physicist like Rutherford, who could give us an estimation of approximate size of a nucleus of any of the atom. Now you cannot imagine how small this distance 10 raised to minus 14 meters may be. So we use a unit in this game that is called as Fermi, 10 raised to minus 15 meters, that is the Fermi, and so that is 10 Fermi is around the size of this particular nucleus of an atom of atom. And as we go from in now periodic table, as we know, all elements right from hydrogen to thorium, uranium, or element number 105. So just put a number of Z there and get the calculation. So easily I can make a table where I can calculate radius of each and every nuclei from element number 1 to the last element in the periodic table. So this entire discussion and analysis, this is called as the Rutherford model. So this model is one of the very interesting, very primary, basic, simple, and revolutionary model that could give us an idea of the nucleus. So how nucleus is there, how nucleus is formed, etc. What is the size of the nucleus, etc. So experimental proof were given, theory was given, and based upon that electronic Rutherford scattering experiment, he showed that in this scattering, this type of scattering is taking place. Therefore, the size of the nucleus can be estimated, and this is found to be 3 into 10 raised to minus 14 meters for element like aurum or for gold, and for all other elements, etc., can be calculated. So try to understand, this is very basic primary theory, over which there may be at least 5 to 10, at least 5 questions will be there in your question paper. So you have to be very careful about this Rutherford model, its outcomes, its basic concepts, its predictions, and everything here. So I am going to ask few questions over this Rutherford model in your coming examination. Okay, so this is first concept we were supposed to understand in this case. Okay, now let's go to the next concept, or the next title of this chapter, next topic of this particular chapter, that is electron orbits. Electron orbits. Okay, now once this Rutherford invented this nucleus is there, then these electrons are said to be around. So around, according to Rutherford, his model of atom was that inside an atom a very small nucleus is there and electrons are around there. So electrons are there. Again, this is a bit different than the plum pudding model, where in the plum pudding model all positive negative charges are anywhere, wherever they want. But here all positive charges are inside the nucleus and negative charge particles. Then around 1897 it were known that these negatively charged particles are nothing but electrons. So people start calling them to be electron, and therefore this model shows that, that means Rutherford model says that all positive charges are concentrated in the nucleus and electrons are around the nucleus. Whether they are stationary or they are in motion, that is not told at all by this particular Rutherford model. And there comes a very difficult situation when we go for such type of stability. So what happens to the stability? So electromagnetic, according to this electrodynamics or electromagnetic theory, whenever there is a positive and negative charge, there must be an electrostatic attraction between these two. So if these electrons are stationary, then these electrons will be immediately attracted toward this positively charged nucleus, and therefore the stability of nucleus is a question. So stability of atom is a problem. According to electromagnetic theory or electrodynamics or the electrostatics, positive and negative charges must get attracted. So immediately once this nucleus is, or this atom is created, all the electrons will be absorbed or will be attracted toward the nucleus, and nucleus will not remain a nucleus, it will get diminished or it will get violated, and therefore stability is the big question in the Rutherford model. So Rutherford model success is that he showed that nucleus is this is this size, this is this constituents, this is whatever that is this is structure of the actual atom is shown by this. But this model is a problem when we think about these electrons, why they are not being attracted by the positive charge nucleus if they are stationary, and therefore people thought that these electrons are now orbiting, they are moving around the nucleus, and that's what the concept of orbiting nucleus came there. Okay, So the concept of this electron orbits is the necessity according to electromagnetic theory. Okay, so you can write here the concept of electron orbits. Concept of electron orbits is necessity of electromagnetic theory. This is the necessity of electromagnetic theory. Okay, so scientists or rather, okay, I will say Rutherford said. Okay, thus electrons are orbiting, according to this model, electrons are orbiting around positively charged nucleus. Electrons are orbiting around a positively charged nucleus. This is what the concept that was given by this further scientist who started thinking over this particular model. So for example, I'll take a very simple example. For example, consider a hydrogen atom. Okay, now henceforth we are going to concentrate more on this hydrogen atom, even in Bohr theory of the hydrogen model, atom model, and so on. So I am drawing a very simple picture here. This is a proton, P plus. I am calling now it proton. Earlier I am calling it to be positively charged nucleus, and this is in orbit. Draw a big picture. Draw a circle. This is to be orbit, wherein this electron, now this is electron having mass me, and this is proton having its mass to be mp, and this electron is revolving around this nucleus in this circular orbit. Okay, so orbit is usually it is said to be circular, so this electron is revolving, and therefore this electron, it has negative charge, that is E minus, this is P plus. So this electron has its motion, this is given to be some V or V bar, and this will get attracted towards this. So this is the force of attraction as shown by here. This is also force of attraction as shown by here. So, and this force must be same, and here I can take this to be distance r, radius of this atom. Electron is at a distance r from the nucleus, and therefore this electron is in motion, it is moving with velocity v, so it has certain momentum me into v, so it has some certain angular momentum, it has some other types of aspects may be there. Okay, so we are considering this model now. So consider this example of simple hydrogen atom having single electron. So here we assume a circular electron orbit. Okay, circular electron orbit for convenience. Now the centripetal force holding an electron in the orbit, it will be given by Fc. Okay, centripetal force Fc is equal to, this is given by, classically it is given by mv square upon r, where m is mass of this electron, v is its velocity, and r is its location or distance from the nucleus. So mv square upon r, this is the simple example, centripetal force. Similarly, there is a force of electrostatic attraction. There is a force of electrostatic attraction. Force of electrostatic attraction, and which is given by, this is nothing but Coulomb's law of force of attraction. Fe is equal to 1 upon 4 pi epsilon 0 into E square. Charge of the electron is E, charge of the proton is also E. Okay, so these charges, now its product will be E square. Now I am just taking their magnitudes and not the direction and all that. So divide by R square. So this is the relation for the electrostatic repulsion or the force of attraction between positively charged nucleus and negatively charged electron separated at a distance given by R. And the centripetal force, because of that, the rotational motion possible is given by mv square upon R. Now the condition for dynamic stable orbit, the condition for dynamic stable orbit, condition for dynamic stable orbit. Okay, this is very simple condition. These forces must be equal, so Fc must be equal to Fe. If there is some imbalance, if Fc is more than Fe, then electron will move away from this nucleus. If Fe is more than Fc, then this electron will get attracted toward the nucleus, and this stability of the nucleus will be a problem. To have a stable nucleus existence, both these forces must be equal to each other. So as I have written these relations earlier, I can get these relations here, and I can write mv square upon R is equal to, now this is 1 upon 4 pi epsilon 0 times E square upon R square. So it's very simple relationship I can obtain from this, and hence velocity relate of V, yeah, and hence velocity V will be, we can calculate the orbital velocity. So solve this. One of this R will get cancelled, this M can be taken here, and we'll get V square is equal to 1 upon 4 pi epsilon 0 into M into E square upon R, and taking square root of that, I'll get V is equal to small e, square root of E square is E, and whatever in the denominator it is 4 pi epsilon 0 M into R. This is the relationship I'll get for the velocity. Call this to be equation number 3. So this equation gives me the velocity or orbital velocity, hence velocity V, that is called as orbital velocity. Orbital velocity, which is given by V is equal to this. Now one more calculation we can do here for the energy. Total energy of hydrogen atom. Total energy of hydrogen atom is the sum of its K, kinetic energy, plus potential energy. So as I know earlier, K is given by 1/2 mv square, mass into velocity square, whereas PE, potential energy, is given, but electric potential between these two charges, which is given by minus E square upon 4 pi epsilon 0 into R. This is electric potential between positive and negative charges. So E square upon 4 pi epsilon 0 R. These are the respective potential and kinetic energy for this type of situation, where there is a positive and negative charges which are separated by distance R. The potential energy is attractive, that's why negative sign. So E square upon 4 pi epsilon 0 R is the potential energy in the case, and K is equal to 1/2 mv square is the kinetic energy of this electron which is orbiting around the nucleus, and therefore total energy capital E is equal to, just write this, 1/2 mv square minus E square upon 4 pi epsilon 0 into R. Now substitute, replace V square. V square is E square upon 4 pi epsilon 0 into m multiplied by r. Okay, from the earlier equation number 3 gives you v is equal to E upon root 4 pi epsilon 0 mr. So I can write v square is equal to E square upon 4 pi epsilon 0 into mr. Replace this v there and you will get capital E is equal to 1/2, m is there, so it is E square upon 4 pi epsilon 0 into m multiplied by r minus E square upon 4 pi epsilon 0 into r. So here this m and m gets cancelled, 2 into 4 is 8, so I'll get next relation is E square upon 8 pi epsilon 0 into r minus E square upon 4 pi epsilon 0 into r. So what is common in this case? E square upon 4 pi epsilon 0 into r is common, so in the bracket it is 1/2 minus 1, and therefore it is minus 1/2 minus 1 is minus half, and therefore I'll get one quantity here that give me E square minus E square upon 8 pi epsilon 0 times r. This is the total energy. That is equation number 4. And remember, this total energy of the electron inside an atom is negative in the sense, so this negative sign is very important in this case. That suggests this electron is bounded, is in the bound state, is bounded to the atomic nucleus, and that's why it is not allowed to move away from the nucleus. It is a bound state because total energy of the system is negative. So whenever there is negative energy in classical mechanics, we say that is called as a bound state. So electron inside an hydrogen atom is in bound state with this proton or positively charged nucleus, and that is suggested by this particular negative sign here. So write one statement. Thus the energy of hydrogen atom is negative. Energy of hydrogen atom is negative. Energy of hydrogen atom is negative, and we call it to be bound state. So it is therefore the electron is in bound state. Electron is in bound state. Electron is in bound state in the hydrogen atom, so it is bounded or binded. Okay, so see here, till now our picture was that this is the nucleus and electron is revolving around this. So this picture we could complete here. This is E minus and this is Ze plus. This is my nucleus and this is the electron. So as good as this is correct. So we have used electrostatics, we have used classical mechanics. So this mu square upon r is according to classical mechanics. E square upon 4 pi epsilon 0 r, that is because of this electrostatics. So both of this, so one is Coulomb law and second is this Newton's law. Both these laws are satisfying all this case, but there is one more very important difficulty because of this electromagnetic theory. Because in electromagnetic theory, whenever a charged particle is accelerated, it must radiate. So there is one more very important principle of this electromagnetic theory that tells or that suggests, that tells you that charged particle, if it is accelerated, it radiates. That is basic fundamental, one of the basic or fundamental concept of this electromagnetic theory. And here inside an hydrogen atom, this electron is in bound state, so it is undergoing a circular motion, and circular motion is always an accelerated motion. So according to electromagnetic theory, if this is the state of the electron, if it is revolving around the nucleus, then it must radiate, and if it is radiate, its orbit must be becoming smaller, and finally that electron should also fall inside this nucleus, and that's what again a question of the stability of the nucleus. So stability of the nucleus is again at a problem. because of this electromagnetic theory. So we'll write in short, very short. According to electromagnetic theory, according to EM theory, if a charged particle is accelerated, okay, I'm going to ask question over this later on. Charge is accelerated, it must radiate, okay, or gives out or loses energy. Energy is radiated, energy is given out by such type of charged particle whenever it is in accelerated state of motion. Here in hydrogen atom, this electron is being accelerated continuously, therefore it must lose its energy, and it must lose its energy, and therefore again a problem of stability. Stability of nucleus, stability of atom itself, not nucleus, stability of the atom or nucleus. Or in some books you will find this type of diagram. Okay, so what is this diagram? This is the nucleus. Electron is revolving in this orbit initially as shown here, and this is an electron, this is the ZE nucleus. This electron comes down because of this accelerated motion, it loses its energy, it undergoes a spiral motion, and it finally reaches to this nucleus. So this must be happening according to this electromagnetic theory. Electromagnetic theory says that whenever there is such a picture of electron in the bound state of this atom inside with the nucleus, then since this is an electromagnetic interaction, or since this is a case of charged particle accelerated, and according to fundamental principles of this electromagnetic theory, this charged particle must radiate, so it must lose its energy, and therefore continuously it will go on losing its energy, and within a very short time this electron should fall on the nucleus, and therefore stable hydrogen nucleus is again a problem. And to overcome this, the concept of stationary orbit, okay, to overcome this failure, a concept of stationary orbits, okay, it's very important word, stationary orbit, was introduced by Niels Bohr. So this particular concept says that whenever electron is in this stationary orbit, it doesn't radiate, it remains in that orbit forever. Okay, so so there are certain orbits, certain possible orbits, certain allowed orbits, wherein the electron, whenever it is found in that orbit, then this electron is not supposed to radiate, it remains in the same state of motion continuously, it doesn't loses its energy. This concept of stationary orbit comes from this concept. Okay, concept of stationary orbit comes from this problem. So this stationary orbit is one of the very important concept that was introduced by Bohr. On the basis of this concept of stationary orbit and three more postulates, he could go to all his theory, and that is what we are going to discuss in the next or tomorrow's lecture when we go for actual Bohr atom model. So try to understand where we started. We have started our discussion from this particular Rutherford concept. So what was the Rutherford model? This was the Rutherford scattering experiment suggested, and practically this experiment were thought. On the basis of that, whatever results obtained, that results showed that inside an atom enough empty space is there. Almost all alpha particles come out of that thin foil, very few get deflected, almost 14%, and very few gets reflected back, and that suggests, or on the basis of that, this particular Rutherford suggested that inside a nucleus, inside an atom, nucleus is such an entity where almost all its mass or all its charges, positive charges, are concentrated in a very small space, and electrons are moving around this. Based upon this concept of this reflected alpha particle, he could find out the smallest approach of alpha particle, and that's what, nothing but the radius of the nucleus. He could show This radius can be calculated by this formula. R is equal to 3.8 into 10 raised to minus 6 multiplied by Z, where Z is the atomic number of that nucleus, meters. So this type of simple calculations and simple derivation as shown here. And once this particular picture was taken, this picture was found to be a problem. Electromagnetic instability will be there. So people started thinking about that these electrons are orbiting inside an atom, and here whenever it is orbiting inside an atom, we can go for this simple picture, assuming that this electron is not radiating. So whatever force of attraction and this particular force of a centripetal force, these two forces must balance. So one is classical force, one is called as electrostatic force or electromagnetic forces. These two forces must balance, and using this balance condition, I could find out this is the relation number 3 gives me velocity of the electron inside an hydrogen atom based upon this model. As well as we can calculate potential energy and kinetic energy of such a case, and that shows this is a bound state of an electron inside an atom. So hydrogen atom is the electron nucleus bound state, and if it is a bound state, there must be radiation loss, and this radiation loss is not there if we assume these electrons are in a stationary orbit. So whenever these electrons move in stationary orbit, they do not radiate, and their orbit is now stable, and therefore stability of the atom is possible. Otherwise, if electron goes on radiating orbit by orbit, one or the other day or some other time, this electron is going to be fall into the nucleus according to this electromagnetic theory. So stability of the nucleus was a big problem, and this stability problem is resolved when we assume there are certain stationary orbit. Now how to take this stationary orbit? For that we are going to discuss later on the second model, that is Bohr atom model, that will be discussed in the tomorrow's lecture. Okay.